And let me see, I guess we will go to Jeremiah next.
All right. Let me see if I can get this to work correctly.
Wonderful. And Jeremiah, I should apologize for jumping in a little early. Mike wrapped up his a couple of minutes early, and so we did just about an hour of Q&As. But so I think that we're actually on schedule, even though we're 10 minutes ahead.
Let me see if I'm not sure which screen is being shared. I'm pretty sure it's okay. It looks like it put a green border around it, so that's good. Okay, I can jump right into this then. Can you guys see this? Hey Tim, can you? Okay, it looks like Mike Hines is saying that you guys can see the screen then. Okay, awesome. All right, jumping right into it. Let me go ahead and present this. I have never used Google Slides before, so this will be my first run with it. Hopefully it turns out well. All right, reactionless electric field thruster is an investigatory cross-comparison of various gradient field drives. So gradient field drives are an interesting concept. They go back to T.T. Brown's work all the way into 1928. The tech has been around for more than 90 years. There's still not a product on the market that you can just buy off the shelf utilizing this technology. All the recent patent applications that have been filed for gradient field propulsion have pretty much been denied or abandoned. And the modern revisions since Brown kind of started in 1989 with Lafforgue, and they've continued to this day. The great thing about this tech is that it's extremely simple in principle, although it does require some dangerous high voltages. And the dielectrics can be expensive in small quantities and hard to acquire. Plus, in order to get really high dielectric constants, which are required for gradient field devices, you usually need industrial ceramics processing techniques. So there have been a few inventors that have pushed through for patent applications. None of these were granted, unfortunately, but they contain really interesting and fundamental refinements of T.T. Brown's work that actually offer us some real and engineerable factors on what we should look for and how we can make these drives. So here's some of the claims. Terence Bates' patent application, a practical high-thrust engine or thruster requiring neither propellant nor reaction force from the environment. It takes advantage solely of the relatively well-known electrostatic field equations between pairs of substantially concentric cylinders or spherical electrodes. Nasikas, which I can't believe is in the audience today, pretty incredible. He also says the method and mechanism for developing a thrust by means of a system consisting of asymmetric capacitors, which are created along a set of charged metallic elements, placed in a non-symmetrical way within a strong insulating dielectric. And so we basically see that there's a consistency here. Even Douglas Torr, an invention relates to an inhomogeneous electromagnetic field. In particular, the generation of these fields will result in a gravitational thrust. So here's systems that can effectively produce a force, freestanding force without reaction mass, without propellant. And what these are not are what we have pictured here. This is a lifter. It's an ion-propelled aircraft. So a lifter accelerates atmospheric gases, and it requires a reaction mass. Gradient field engines do not require that reaction mass. So here's a basic overview of how these devices work. We can see here that we have on the top half here a high K, high mass dielectric, and on the bottom half, a low K, low mass dielectric. These two dielectric layers with different masses and different K factors are sandwiched between two cylinders or two spheres. So the internal cylinder or sphere forms one electrode of the capacitor, and the outer forms the other. This is an end view we're looking at. Of the inventors that have pumped these devices out, we have quite a few variations from Lafforgue to Terence Bates, Douglas Torr, Nasikas. And if you take a look at all these designs, you basically see something very similar. We have either two different dielectrics like we have in Terence Bates and Douglas Torr, or we have a gradient dielectric like we have here with Nasikas and T.T. Brown. And these same structures, like we see here in figure 5, and in this picture over here, we can stack these structures up in big arrays in order to amplify the force according to the inventors. So everybody's kind of got their own theory on how this stuff works. Brown's been around for a while, and he is pretty much the initiator of this technology, one of the first people to ever discover and come across it. But it's been a big issue of speculation forever, exactly how Brown's thrusters supposedly worked. So Bates says that the key to making these devices work is by having a very high K dielectric on one side and a very low K dielectric on the other. Well, Tor emphasizes that it's not just the K factor of the dielectrics that matter, but it's also the mass difference in the dielectrics. Brown says that it's mainly about the shape of the dielectrics and the shape of the electrodes, or how massive they are. And Nasikas really tells us that we need to minimize the distance between our wavy capacitor and our flat plate and maximize the potential between those two plates, which means we need a very high potential insulating dielectric. The good thing is, although the theories kind of disagree with each other, they all do agree in some ways, and that is they all require asymmetric electrodes or asymmetric dielectrics. They all state that a higher K equals greater force, and they all make use of gradient fields. So Jean-Louis Naudin tested this idea that we see in our pictures here. He tested this idea with a foam block covered in aluminum foil and a piece of high density foam on one side of this material and air gap as the other dielectric. Now with this system, where you have foam as one dielectric and air as the other, in a system which has symmetrical spacing between top and bottom, there is in fact a small thrust produced. However, if you fill that same gap on the right picture here with that same K, same mass dielectric, the force completely goes away. So this was a great way to actually test, and I'm glad that he verified this. So in terms of my testing in gradient field engines, I just wanted to point out some common measurement errors that I see people make all the time, and that is having your test device located on the scale, on the countertop or the table, just inches away. You have electrostatic forces that are in the kilovolts range, and they have significant attraction to all nearby surfaces. So here's one of the setups that I use. I have a Faraday insulated scale that's completely covered in aluminum and copper tape, which I set on top of a grounded shielded platform. I suspend my test sample from a suspended platform, which is at least 2 feet or more away from the floor, walls, and the scale through these thin wires, filament wires. I make sure that my HV source, which is a multiplier built on board this test stand, has a very, very short lead wire from the output going to the test sample so that we don't have contributions of wires being attracted to nearby objects and we don't have leakage currents that are present. So all these things help us get a much more reliable test, and they help reduce the sensitivity of electronic or digital scales, which are really a problem when trying to take measurements of electrostatic systems. So Alexander Frolov definitely deserves a mention with gradient field drives. He came up with a very simple system of 2 electrodes mounted on a piece of dielectric material, the other side open to the air, and some kind of divider between those 2 pieces of dielectric. So I tested a variation of this device of what Jean-Louis Naudin called the Frolov's hat. The device statically weighs 82.2 grams, and when it was charged to 80,000 volts in my test stand, 2 feet away from the scale, I did not receive any forces above 0.1 grams, which is the minimum resolution of my scale. So if it did produce a force with no corona, no ionic leakage whatsoever, then it was below that resolution. So we know if it produced a force, it was very, very small. However, our other affiliate labs had also tested this device, and they did receive very small forces in the prediction, in the direction predicted by Alexander Frolov. But we have not concluded the testing on Frolov's hat yet, and we're still looking into other alternatives. Ultimately, we don't think that the use of air as a dielectric is a very good solution for pursuing these drives, so we're moving on to better ideas. I also tested Lafforgue's idea of a directional thruster. In this case, I used a wax mixture with titanium dioxide powder. And as you can see, the design I have here pretty much matches the geometry of what he's patented. I did reduce the length of the pole legs a little bit because according to Jean-Louis Naudin, the poles did not need to be as long as pictured. But in this device, I was noticing 2-gram spikes. I started out at 0 volts and ramped it up to about 65 kV in 10-gram increments. And every time I would ramp up, I would notice a little spike of thrust, which would quickly go away. And finally at 65 kV, I started breaking down. So I retired this device. Wax is a pretty crappy dielectric, being honest. And so I'll be moving on to better experiments as well. I also tested other gradient field thrusters like this one pictured on the left here. This is a T.T. Brown style tapered dielectric. And this system actually does produce a very small thrust of about 0.05 grams. Again, it's wax and titanium dioxide, so it has a pretty low K, but it has a reasonable dielectric insulating factor. So it's not a force strong enough to really pursue. So we're giving up on these types of single dielectric gradient field drives for the time being. I wanted to test, though, the concept. So in T.T. Brown's electrokinetic apparatus patent, he proposes this idea that we see here in figure 8. Here we're looking at a metal toroid, that's part 48, with a metal ball here. And this ball is attached to a high voltage power supply, the other side attached to the toroid. And by moving the ball into or out of the axes of the toroid and keeping the charge the same between the two, he claims that this device will produce a force 54 or 53 in this direction. Now, in my case, I did build a small device like this. I charged my sphere to a negative potential and the toroid to a positive potential and set it up on the scale. In order to keep wires out of my system, you can see here in the picture on the left, is a small 25 kV battery powered PSU. It has a small photo trigger right here around where my arrow is. You can shine a flashlight on it and remotely activate it. So in this case, I don't have any wires being attracted to anything. And then here you can see that power supply integrated into the test device case. So in my test results, I was able to receive a small force of about a weight loss of 0.25 grams upwards, with the ball facing up when it was negatively charged. And if I flipped it around on the scale, I received a downwards force of about 0.12 grams. The difference between those two measurements is a very interesting phenomena that I'm still looking into. And again, this test setup needs to be put on a torsion balance because I don't feel like I had adequate distance from the test device and the scale. But it looks like Brown may have been right in his patent, so this is looking positive so far, and continued tests are required. Now, it's not just, crazy fringe scientists looking at these ideas of electric field propulsion. NASA gave it a whirl, and in 2000 and 2001, Jonathan Campbell received 2 patents for an asymmetrical capacitor thrust device. And he says, it is well established in the literature that a force or thrust may be generated by a capacitor charged to a high potential. Although there are different theories regarding the basis for the phenomena, there is no dispute that a force is generated by capacitors under such high voltages. But he also admits there is a need for further improvement in the module construction to enable thereof use in atmospheric propulsion or propulsion in space. And this goes in concert with this device that was patented by Jonathan under NAFTA, where a lot of people disagree that this device actually operates by direct forces and say that it's still an ionic force. So there's a lot of debate open on that yet. And we are hoping to close that debate with some better devices. Who else is doing the research? Well, I have to mention Hector Serrano, founder of Gravitech Incorporated, has been developing the technology for a super long time. In 1993, when he was deployed in the Navy, he started playing around with field propulsion technologies by acquiring a hefty, nice CRT power supply transformer from his EE Navy barracks crew. In 95, he finally retired, moved to Orlando, and started shopping at a little hobby store called Skycraft for parts to construct his first field propulsion drive. And then finally in 97, he officially incorporated Gravitech. And by the following year, they had already been doing research in their garage, and he managed to acquire some people to help him along the way. Now, almost 28 years into his research, the newest SFE Gen 3, that's his newest thruster design, is just weeks away from testing. So I've been watching Hector for a long time to see where exactly the SFE is going. And now that we're just weeks away, we'll be watching pretty closely to see where Gravitech is going to take this tech now. And Richard Banduric also needs huge mention here. He and his team at Field Propulsion Technologies have been working hard to develop groundbreaking propellantless propulsion spacecraft technologies. They claim to have several known working products for spacecraft propulsion based on the interaction of electrodynamic fields using only electrical power. So do they have legitimacy? Absolutely. They were granted several patents on multiple variations of the technology. And DARPA thought they were interesting enough to land several contracts. So because they seem to have the credentials and because this technology looks very promising, I'm personally in the process of independently replicating Richard's earlier tech, his static displacement field drive, and I hope to have test results on that soon, but we'll cover more on that later. So if fuel propulsion engines or gradient field engines could actually be produced correctly, according to some of the inventors, what kind of forces could we expect? Well, this is actually pretty exciting because if we use some high K dielectrics like 20,000, which right now CCTO gives us a 200,000 K factor, so 20,000 is nothing unachievable. Then with a small micron-sized cable, we can expect that cable to lift more than its own weight. And here he says, since the weight of the cable is less than the net force produced, there is effectively no limit to the number of cables that can be used for lifting purposes because they lift farther more than their own weight. Now that's a hell of a claim for an asymmetric capacitor to lift itself and then some. But it sounds like we're getting into the possible regime of being able to lift their own power supplies. First, we need some high K dielectrics, though, in order to do this. And what do we have available for high K dielectrics? Well, I threw together a chart of everything that we can pretty much buy on the market today. And depending on whether Nasikas or Tor or Bates or Brown are correct, we have a variety of different materials to choose from. So if it turns out the mass of the dielectrics needs to be the most different, lead magnesium niobate at 975.7 grams per mole is a pretty massive dielectric that would be the ideal thing to use. But if the K factor is really critical, then we can use calcium copper titanate as one of our two massive high K dielectrics. And if it is just the density that counts, according to Brown, then we can use lead monoxide, the heaviest of the dielectrics I found at 9.53 grams per centimeter cubed. I guess it really depends whose theory is right, if anyone's, and which one will be experimentally proven. So this is what I've started so far. I've acquired some parts for a preliminary electric field thruster. I managed to find some hemispheres online, which you can simply purchase. And this is great because it makes them easy to replicate if this device turns out to work. So you can just buy stainless steel hemispheres and hollow spheres online for pretty cheap. Here on the left picture, I've taken one aluminum foil hemisphere and a dresser drawer handle and encapsulated the low K, low mass dielectric, which is just epoxy in my case, on one side. And on the upper side, I'll be adding a mixture of CCTO and epoxy. So to figure out what kind of gradients I'll be looking for, here we can find out that you can actually make your own high K dielectrics yourself by mixing high K dielectric powders with regular epoxies. So in this paper here, there's a pretty good instruction manual on exactly how you can pull that off, but it does look like it's possible just to mix in dielectric powders with epoxies, and you can do this at home. And so according to what I've calculated out, if I use the materials that I've already got here, CCTO as a dielectric and EC690 as my epoxy mixture with these stainless steel spheres, about 60 millimeters in diameter for the ID of 1, 30 millimeters in diameter for the OD of the center sphere. I have a dielectric ratio of about 6.16 to 1. I have a K factor of about 600 to 1, and I should be able to get 150,000 volts into this device, which is well beyond the noise floor of forces that we'd expect to see. I'm not the only one doing it. We have several affiliate labs. Wayne and Nam are both working on the cylindrical capacitor version of this technology. They've been doing really great work, and we're waiting for test results coming in soon. And well, if we can use asymmetrical capacitors like this to produce a thrust, what might they be used for? I guess I'll leave that to everyone's imaginations. So, is it possible to produce a force without reaction? Richard Feynman seems to think so. And in his lecture 17.4, he talks about an interesting idea where a non-zero momentum can be transferred from an electromagnetic coil attached to a plastic disc with charged metal spheres around it. And so basically what he describes here is that in this solenoid with a battery on board, all this being part of the same assembly, the solenoid slowly builds up a current flux over time. And as it begins to build up its field, that field has an interaction with the electric charges in the charged spheres. Now say the circuit is suddenly disconnected. Now that coil and all the electromomentum that was flowing through it suddenly stops. So the momentum that was stored in that field has to be returned. And because the field is no longer tied to the coil itself and it's been radiated effectively because there's a very fast amps per meter change, there is a Lorentz response to the charge on the spheres. And as a result, this entire device should theoretically rotate. Now, it doesn't make sense how you can, basically blow your own sail, but in this case, he gave us a mechanism to do it. And so he describes the mystic circulating flow of energy, which at first seems so ridiculous, is absolutely necessary. There really is a momentum flow, and it is needed to maintain the conservation of angular momentum in the whole world. So if he's right, basically what it means is reactionless force is indeed possible, and we have a hypothetical way to pursue it. So other things that I've done in propulsion research recently, I have developed a little electrodynamic displacement current tractor panel. So what this thing can do is attract any solid material to its surface, both insulators and conductors. It demonstrates a universal high-frequency dipolar electrostatic field attraction of any matter, and it's constructed out of trash printer parts. Anyone with skills can build one. So I've got a little video demonstration of that. Hopefully it plays. Now I know I don't have sound configured to come through, but on the left there, we have that plastic ribbon cable panel, and on the right, we have a piece of thick plastic material that's being pulled towards it. Here I have some pieces of plastic that I'll be picking up just by pressing the power active button, and the second power is let go. You can see it drops them. And so it's not just lightweight plastic materials that it can pick up. Here's a heavy piece of glass, 1/8 inch thick. And as soon as I press the button, it's like a magnet for the glass. Let go of the button and it immediately drops. So what this really shows you is that gradient fields can be utilized to perform real work or exert forces on just about any variety of materials. And engineered correctly, these can have real practical applications. So we wanted to play around with other interesting effects too. We were looking for high impulse power to see what kind of phenomena we might be able to capture, looking for non-zero propulsion forces. And we constructed a huge impulse generator. We just sort of said we stuck a lightning bolt in a box. She can do 9,000 joules at 500,000 amperes, 1,800 volts discharge. It charges at 1,850 watts, 3 pulses per minute. And in terms of the inductance discharge loop, it's about a 16-inch wide, 1-turn loop. So it produces strange effects like softening wires that become solid again. And in the next slide, you can see what it does. On the right, we see a piece of steel wire that was unfortunate enough to be between the terminals. On the left side, you can see the 2 discharge terminals of that impulse generator. And in the middle here is just a quick drawing to show you one of the weird things that happened. We had a piece of 12-gauge solid wire between the terminals. When it destroyed itself and flew apart, that solid piece of wire, if you can see my arrow here, followed between these pieces of wood, actually went between the plywood door and the wood frame, took a 90-degree bend without denting the wood, snaked out, and then was sticking out about 3/4 of an inch on the other side. It didn't damage the wood at all. It didn't puncture through, and 12-gauge wire is actually rather hard. So even moving very quickly, I would have expected it to, impel itself, but that's not what it did. Which tells me this wire was in a very, very soft state for one reason or another when it was moving through the door. So it tells us there are interesting things to look into when it comes to high power discharges, and we might be able to exhibit some strange properties of material under these high current effects that we'd normally never see. So I'm going to skip over this real quick, a search for invisible forces. But I will just cover it real quick. When I was younger, I built a 160,000 volt multiplier with a large 6.5-inch diameter discharge terminal. And I noticed a strange phenomena that if my hand was about 1 foot away from that terminal, and I would have suddenly discharged it, there was a pushing force, a very quick push away from that terminal that was detectable by me or anyone else that was standing nearby it. And I thought, that's rather strange. I would expect it to be, pulling towards, but I wouldn't expect the push. And so this relates back to the 3M invisible wall problem. In 1980, David Swanstrom, who works for 3M, he was an investigator for 3M trying to solve some weird electrical problems that they had. He was called into a 3M plant because one of the huge conveyors of polypropylene film they were using to make tape was exhibiting strange properties and freaking out the employees. So they couldn't quite explain to him what was going on over the phone, and he decided, well, I'll take a visit there and check it out. When he checked out this film material, he had a voltmeter to see what kind of electrostatic charges it was building up, and noticed that it pegged his meter, indicating to him that it must have had over 1 million volts on the belt. So he decided to walk underneath this roller, which came up the left side, went over the center of the doorway, and down the right side, a total of 21 feet wide belt, 21 feet high, 20 feet over, and 21 feet back down. This is a huge belt with tons of charge. He noticed that as he walked underneath this belt, he started to feel pinpricks on his arms and legs. His hair stood on end, and as he reached about the very center of the belt, he got stuck in what he described as an invisible web, almost like a force field, and he describes having to actually peel himself away from it to walk back out, almost like it was a force field on Star Trek. So what the heck happened that day? So polyfilms can develop a huge amount of charge. I'll show you a quick video here. Here we can just see several foot long lightning bolts jumping across the surface of this polyethylene film being unspooled at a not really all that fast rate. And so you can imagine something moving at a reasonably high rate, unspooling quickly, could develop easily millions of volts of charge. And that's a hell of a lot of charge moving really quickly. So Richard Banduric actually offers us a possible explanation for the phenomena and a way to engineer it. And what he describes to us is that when you have charges trapped on the surface of a smooth plastic and you move those charges very quickly, those charges are effectively open circuit. They're not part of a closed circuit loop. And so when they're moving very quickly relative to a stationary observer, they get geometrically amplified, and the electric fields that they appear to have become significantly stronger. And because these electric fields are relativistic fields and they don't actually exist from the reference frame of the particle themselves, they don't have an equal and opposite force. So this is one way that the force field might have worked. Now, in pursuit of trying to figure out how this could have worked, I decided to build a small version with a piece of polypropylene disc material I pulled from a TV. And although the disc was much smaller than the 3M belt, there was a very weak but perceptible force near the surface of the disc, only when it was rotating. That wasn't present when the disc was stationary. So I charged half the disc up, and on the picture on the right here, we can see the scope trace showing an AC waveform as the charged half of the disc moves past the pickup electrode. Now, as you increase the speed of the disc, naturally the amplitude peaks of the waveform go up, indicating to us there is some geometric amplification taking place. And that's enough data in hand to continue with results and experiments. So if you do charge the disc up and allow it to discharge, you get quite the fantastic snap out of it. I'll play that one more time in case you didn't see it. Here I'm depositing 160,000 volts on the surface, and eventually it gets too high and it leaps around the edge. So the big difference between my system and what actually happened at the 3M plant that day is mine is moving at 4,188 feet per minute. Well, the 3M belt was only moving at 1,000 feet per minute. They had possibly over 1 million volts of charge on that belt, and I only have 130,000 volts of accumulated potential. Their belt was 21 foot wide, and mine is only 16 inches wide, and they had 3 interacting flat surfaces at 90 degrees to each other, each with its own independent electric field, and all those fields would have been intersecting. Whereas in my test, I just have one single disc that only has one electric field, plus, in the 3M's case, it was almost 80% humidity that day, and a rather high temperature of almost 80 degrees. And so in my case, I'm testing at about 20% humidity and about 75 degrees. And apparently the humidity was a really critical factor, as later in the day, David Swenson reports that when the humidity goes up and the temperature goes up, the effect starts to diminish. Other experiments that I'll cover real quick. I did build a Boyd-Bushman magnetic beam amplifier. He makes some pretty fantastic claims that this device can amplify magnetic fields into a beam form, and it can generate electromagnetic pulses, disrupting circuits that use transistors or other sensitive electronics, and that it can extend the length of a spark discharge from a Van de Graaff generator. So I constructed 2 of these beamers, each of them with an opposite polarity, and I added modulation coils. On the left, we can see a modulation coil between the rear magnet and the rest of the assembly, and on the right side, we can see a wrapped modulation coil that takes place of the rear magnet. Here's a pulse power supply to really slam the modulation coils with lots of energy, looking for any changes in the magnetic field geometry. And then here's a basic test setup that I did. I hooked one of the coils up to a scope that I placed between these 2 points here. And in this coil, I modulated it with the impulse bank. And what I measured on my scope was a pretty insignificant fluctuation of voltage. It certainly was no electromagnetic pulse. And actually what I got out of Boyd-Bushman's claims here were that I didn't get any pulse amplitude beyond what would have happened with my coils if there were no beamers in place at all. So clearly I'm doing something wrong, or the claims of the patent aren't quite as they seem. So if anybody has advice on how Bushman's beamer was supposed to work, it doesn't appear to me too obvious that it works exactly as prescribed. So I have to give up on this project for now and wait for better information. So updates on the static displacement field drive of Banduric, and this will be one of the last things I cover here. Now, pictured above, we have Richard's original, or one of the original field propulsion technologies drive prototypes. And so basically what a static displacement field drive is, it's a motor with one disc attached to it and a separate disc of a separate material fixed to a frame on the other side. A high amount of charge is placed between these parallel discs, which act like parallel capacitor plates. And because the discs have 2 different fields, 2 different physical surfaces and constructions, there is a very big difference in the complex electric field produced by those disc materials. So when you rotate them, you end up developing a torque or a load on the rotation of one of those disks, which then is converted into an axial force. And without getting into too much detail as far as how that works, let's just go into what I've covered so far with it. My first failed attempt, this is the device that I constructed over at Falcon Space Laboratories in collaboration with Mark, and it was hung on a torsion balance. This system had a couple of problems. First one is that the dot product disk, one of the most important components in this system, didn't hold a large amount of charge and the material was too thin. The second one was that I used an external tube isolated power supply, and it was connected to the device with long wires, and long wires are terrible for this application, so that had to go. In the new version, I'll be replacing all that with an onboard integrated power supply. And instead of using batteries to power the tubes like Richard did, in this case, I'll actually be using an isolated 20 kV transformer to power those tube filaments since they work just fine off AC. And then I can regulate and drive those to keep constant cathode current from an onboard driver circuit. I'll have also built into the device onboard current and voltage meter plus onboard tachometer. So this means there are no wires connected to the device. It's entirely optically triggered and battery powered. So again, eliminating wires out of the test stand is ideal because we don't have contributions from wires being, tensioned or pulled or charges on anything. And so in order to make the dot product disk, the thing that actually holds the huge amount of charge necessary to generate forces in the system, we're going to mix some metal powders with epoxy mixtures. And in this case, I'm just using some fine nano powder and max GPE epoxy, which is what Richard used. I needed a sonicator. They're kind of expensive and I didn't have one in time, so I tossed a simple 100-watt sonicator together and this worked beautifully. I just simply epoxied a transducer to the bottom of a glass. So if you need a sonicator in a pinch, this works great, just FYI. Once the epoxy and metal is mixed together in the sonicator and the mix is homogeneous, it gets poured into a circular mold that's sprayed with some easy release. So it just peels right out, and then that is vacuum degassed, cooked in a oven at about 65 degrees until it's cured, and then what you end up with is a composite disc of metal and epoxy that holds a pretty decent amount of charge. And to finish that disc off, I encapsulate the entire thing between 2 layers of polypropylene film, which is a very good material because it tends to have a very low leakage current. And then around the outside, it's totally encapsulated in epoxy so that there's not a single point on this thing where it's exposed to air. I've built several variations. They all tend to work with a little bit characteristics, but none of them are great. And I actually am still not quite happy with what I have for dot product disk, so I'm working on that to this day. Cross product disk is equally important. This is a smooth disk that allows us to amplify the cross product of the complex electric field. And so in this case, you want a smooth material that's able to be spun very fast. And I'm using fiberglass with a highly polished copper clad surface. And I'm using a 3-phase ESC-driven motor. I can hit about 15,000 RPMs in this case, which is significantly higher than my 9,000 to 10,000 RPMs on the last design. And so this should be good. And concluding thoughts as far as what we're working on today. Electromagnetic science is full of non-intuitive concepts, things that seem contrary to common sense when from what you were taught in high school physics. But consider, for example, how 2 charged particles interact when one is moving and the other is not. Basically when they're in different frames of reference. And then my favorite quote probably of all time, which is, if it doesn't matter, how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong. And Richard Feynman is right. If we can't experimentally test these ideas, if they're just theories and they look great on paper or they're mathematically perfect, but there's no way to actually bring it into the lab, in this day and age, it kind of doesn't matter because those things are going to get us there, but what we need is results now, and we don't have enough experiments going on. So really, I just want to encourage everybody, when you're in your lab working or you notice something weird and unusual or quirky, pay attention to it because you never know which one of those observations might be the key to the next breakthrough propulsion technology. So all right, folks, that's pretty much it for my presentation. I hope you enjoyed.